Welcome back to the hyperbolic coding chamber. We are back once again. We are now the anti Lil Mustard Association. We were gifted a problem from Lil Mustard by the name of ones and zeros, but this problem has been bullying us. I'm convinced that this problem has not been solved, and that the LeetCode moderators. Okay, yeah, there's a plot here, but yeah, I actually was doing some reading, doing some thinking on my blue lock power level, and on ones and zeros, I think we're gonna pause on this problem today, only because I actually also gonna do a shorter session because I was just reading the ADM and doing some algo grinding for about an hour, so gotta balance the actual LeetCode time and the supplemental reading. I think I can definitely see with this problem that I need some more supplemental reading. So that's what we're doing. So the session is a little shorter, but the work was still done. That being said, we have some comments here. Also, this browser is the Arc browser. We have some comments here. Website lover. Website lover says, keep it up. Feel strong, man. We have from Joseph Reps, favorite anime. Oof. How much time do you have? We need to link on this. True. Yeah. Favorite anime. Tough answer. Tough question to answer. That is a tough question to answer. I feel like it always gets bifurcated, if that's a word, based on a bunch of different categories like nostalgia factor, old-timey factor, most innovative anime between 2005 and 2010, then 2010 to 2015, and 2015 to 2020. Yeah, it's pretty crazy, though. Some favorites right now this season, though, Blue Lock is kind of a banger. Kind of Flames, Eye Shield 21 vibes. Also, Kuriko's Basket. Also, Slam Dunk. Also, Eye Shield 21. So, pretty dope. What else is going? Yeah, Mob Psycho is going crazy this season. Looking to see a movie from the studio animation team, so that could be pretty cool. And yeah, there's a lot of good ones. I would say Made in Abyss is also really good, and then Cyberpunk Edge Runners is just flames. We have a comment from I'm Just That Guy. I've been on hiatus, my brother. Welcome back, brother. But I am back better than ever. Glad to see that you're still consistent. Feels strong. Sometimes we must walk or sit to run. Feel strong, man. And then from Alpine Yardstick in camel case, Alpine Yardstick 222. Keep grinding, brother. Will do. You too. So we're going to do a slightly shorter session today. I'm not exactly certain if it's day 145. They're kind of blending together. I also don't know where I am. But we're just going to jump into it. Not many philosophical reflections today. I have some thoughts about some algorithmic trainers, but it remains to be seen whether or not that will be the play. That being said, yeah, I was just reading up the ADM for like an hour, if not more. So I can't also do an hour and a half of LeetCode. That would be insane. So we're just going to do 30 minutes. And then I'm hoping tomorrow, I have high hopes for tomorrow. I really do. I think I have high hopes for tomorrow. Actually, maybe we should still do ones and zeros anyway, so that I can contextualize the problem with the supplemental reading. You know, we'll do it anyway. I'm pretty sure we won't make any progress at all, but we'll do it anyway. So we'll pour another 30 minutes into it just to stain the problem into my brain. But I'm just going to jump into it now. So I'm going to start the countdown at 30 minutes. Okay. Before I read the problem, I'm going to try to remember what the problem was. I think given ones and zeros, we're given an array of ones and zeros. We're given an array of ones and zeros and an integer m and an integer n. And the problem is asking us to pretty much find the largest subset that we can create using at most m zeros and n ones, I think was the problem. You're given an array of binary string strs and two integers, m and n. Determine the size of the largest subset of stirs such that there are at most m zeros and n ones in the subset. I think we said it opposite, but m maps to 0 and n maps to 1. A set X is a subset of Y. A set X is a subset of Y if all the elements of subset X exist within set Y. Or are also elements of Y. So we can see here, we have 1, 0, 0, 0, 1, a bunch of these different binary strings. We're pretty much looking for the largest subset such that we have at max m zeros and n ones. And the max we can create here is actually 4, because we do 1 and 0 here. We have 4 ones left and 3 zeros left, and then we do 1 and 0. We'll have pretty much have 4 zeros left and 3 ones left. And then we can do another 1 0 here. We'll have 3 and 1 left respectively. Then we can add this one here, and then we'll pretty much have used up our entire block pretty much of zeros and ones. So we'll have 4 total subsets. What's interesting though is I'm kind of seeing this as we tried a version that had to do with the map. In the map we loaded pretty much, what's it, a map based solution? Oh no, it was a greedy solution. We tried a greedy solution, right? So we tried to sort the array based off length because we pretty much want as many individual elements in the array as we can while reaching at most m zeros and n ones. The problem there with the greedy approach was that by not abstaining from instant gratification of taking the locally optimal solution, we end up actually making the incorrect choice. And I think the test case that failed that looked something like this, where we'd have like 1 1 1 1, which was the shortest string, but we could actually create an even longer string by doing something like this. So if we take 1 1 1 1, you know, let's just say given m is equal to, let's say m is equal to 3, right? And n, which is 0, is equal to 5 or something. Or let's just say it's equal to 9. If we take this first one here, right? If we take this first one here, because we sorted it by length, we end up actually being oh yeah, let's make this one. Actually, I think it was something like this. Oh, right. We end up returning, yeah, this is exactly the one. We end up returning 1 here because of our greedy approach. We sorted the array by length. We take the greedy approach of pretty much taking 1 1 1 first, right? The issue, however, ends up being that if we take 1 1 1, we subtract 3 ones from m, we end up with 0, and we end up being unable to pretty much take any of the remaining elements, right? So the largest subset we return is actually 1, right? Because we're doing a locally greedy option. But the thing is, if we were to switch our angle, right? Let's just say we started with a different element, like 0 0 1, we can take, okay, 1 of this one, 1 of this one, right? And then 1 of this one, and we'd have to stop, but our largest subset is now 3. So that's where we were failing. I think it passed pretty much all of the, we had pretty much optimized it down to pretty much, it was like 6 test cases remaining, but there's no way it's just an issue with the algorithm itself, even though the greedy solution gets us far, but not far enough. So now the way I'm seeing it is actually a graph problem, right? Ideally, I think there's some DP here, but Dijkstra's algorithm, which is an algorithm for shortest path, also has a DP-like nature, right? Because if you're trying to get the shortest path between 2 vertices, let's just say a given vertex S and an n vertex T, right? assume there's a vertex x in the middle, right? And if we assume we have the shortest path from S to T, right, then there cannot be a path. Then the path from S to X, pretty much we prefix our paths with the optimized solutions to build the shortest path, which is pretty much saying that there is no shorter path for the prefix S to X, right? If S to T is the shortest path, S to X, I'm getting confused, but S to X must be the shortest path. Otherwise, it'd be a shortest path with a different prefix. So there's a DP-like nature to Dijkstra's, which could lend us to solving this problem. But yeah, let's see if we can. And we're talking about the shortest path here, but I'm thinking for Dijkstra's, we're actually going to do the longest path instead. So if we change the desirability of how we rate the desirability of edges, which is the big difference between pretty much the main difference between Prim's algorithm and Dijkstra's algorithm, I think this could be solvable. So to see this as a graph, we pretty much, Dijkstra's algorithm generates the shortest path between S, which is the start vertex, and all of the vertices. We could pretty much, if we could generate this parent array right here, I think we could pretty much just search through, right, the parent array, going through, right, and subtracting zeros and ones, right, until we can find the largest subset, or the one with the most vertexes that don't break the M and N rule. I think one issue though is using Dijkstra's for this is that how would we actually rate the desirability of an edge of a vertex? If we have 1, 1, 1, right, and 0, 0, 1, why should we choose one over the other? This might be the main issue with using Dijkstra's for this problem. One thing I'm thinking is string length, but that would be no different than the greedy. Actually, maybe it would be different than the greedy approach. So you'd have 1, 1, 1, then 0, 0, 0, 1. And in fact, the distance array here would store for every vertex the distance between all other, the distance from start. Another thing we could do is run Dijkstra's for every vertex in the array, which would give us n cubed time, which might not be the worst thing. which might not be the worst thing. The distance array pretty much stores distance a vertex is from start. Or distance the vertex is from start. These would technically all have the same distance. Yeah, I think this might be fine actually. We can rate the desirability of an edge based off string length, and then we could just run Dijkstra for every vertex. Worst case, this would be n cubed time Yeah, the distance the vertex is from start. Yeah, if distance array stores distance the vertex is from start, which I think is true, then it does not actually make sense that we pretty much have to run Dijkstra's multiple times. It should be n cubed. But it's interesting that even if you consider Dijkstra's here, it's unclear that you actually end up with the path that actually gets you the longest. Yeah, it's unclear that you would actually reach the ideal location here. Technically, if we use string length, need more thoughts about this. If we use how to evaluate edge, how to decide edge weight, string length. If we use string length, technically this is a connected graph, so even if you start here at 0, 0, 1, you would never ever choose the other two 0, 0, 1s, even though they're longer. You would just choose 1, 1, 1. But you couldn't choose 1, 1, 1 after choosing 0, 0, 1. So maybe the graph is not completely connected. Maybe the graph is not completely connected. We can use string length, but neighboring edges will change. Neighboring edges will change based on m and n. Example: if an element has a shorter length but would make m negative, no path. That way we could run Dijkstra's each time for each element as a starting node, and the output would actually be different. So I think that actually would work. Here we have a Boolean array in tree, which we can just make lowercase. What this actually represents is the vertex in the tree yet. All right, and parent holds paths through the tree. We'd pretty much want to encapsulate this in a function later on, because we're going to call it multiple times. All right, we might need some other variables, for example, a counter, maybe not, maybe w for the current vertex we're processing. To do that, we can actually just do that up here. Right, we'll create a variable v, right, and this is actually going to be current vertex to process, right. V is going to start at 0, or maybe we'll pass it in. And here we're setting up all the values for the 3 Boolean arrays. Right, and typically, right, since the distance array stores the distance for the vertex, stores the distance from start for a vertex, right, distance sub v, or our distance v, our distance from ourself would actually be 0. If we're doing regular shortest path right now. Right, that's going to init our variables, right. From here, we pretty much always want to iterate while the vertex that we're searching for is not in the tree. We want to evaluate our neighboring edges, but not after saying that the current vertex that we're processing is now in the tree. We're going to evaluate the neighboring edges. Wait, can the graph change? I don't know if the algorithm works if the graph can change. Let me revisit this. Neighboring edges will change based on m and n. If neighboring edges can change based on m and n, I feel like this kind of breaks the statelessness of Dijkstra's. Nonetheless, it would be cool to implement this anyway. So you want to evaluate neighboring edges. Iterate over neighboring edges. Just for this case, right, if we iterate over neighboring edges, we probably want to skip ourselves, right? And I forgot we also need dist, which is going to be our best current distance from start. It's going to be used later on though. Down here, so we'll set dist equal to infinity before we iterate over all the vertices. We won't need if v does not equal w, because our main case is also going to make sure that it can't be in the tree if we're considering it being our next node to process. Additionally, what we're looking for, right, is a node such that dist, which is infinity, right, dist is greater than, let's just say, distance sub w. It'd be actually kind of confusing to use w as the variable here, because w is for actually, no, it makes sense to use w here. The issue is actually using it here. Right, we're going to say dist is equal to distance sub w, as well as v, right, is now going to be equal to w. So we're pretty much looking for the node with the shortest distance here. So ideally, we would probably swap this for the one with the largest distance, and we'd probably set distance equal to negative infinity to do longest path. I'm going to iterate over our neighboring edges. If we iterate over our neighboring edges, iteration over neighboring edges, which is what we're doing. Just so happens to be that the graph is almost entirely connected. So we're iterating over the entire string's out length. So, and distance of v what I do know is that the node that we would choose, distance sub p, would get the value of distance sub v plus the weight of the edge, which would just be stirs sub p dot length. But v does not equal p. But what if distance? I forgot we would also say that parent. The spacing so off. We'd also say that the parent of vertex p would now be v. And v does not equal p. And distance I'm going to iterate over the neighboring edges and choose the edge with the shortest weight. That's the case, we usually do something like distance sub v Maybe p doesn't make any sense at all. Maybe it does make sense for this to be w. And distance sub w, which would be the neighboring edge, is greater if W, which is the distance array, stores the brain is mush. The distance array stores the distance from a vertex is from start. So if distance of W, which is likely infinity right now, is greater, distance of W is greater than distance sub P, which is where we currently are, distance sub V, which is where we currently are, plus the weight of the edge, it would mean that distance sub W, what does that mean? It means that distance from start. Oh, it means that distance sub W is an inferior path because it's greater than the index that we currently are at, which is V, which is the distance from the start vertex, plus the weight of actually getting to W, which means that the current distance to the current, whatever path we took to get to W to set the value there, must be worse than our current path. So we can say, we'll set this equal to distance sub V plus distance sub weight. Parent of W will be V. Now, if we ran this, we would generate the distance array, which would have or the parent array, which would have the shortest path starting from S, which is vertex 0, to all other nodes in the string array based on string length. Based on string length, I'd like to run this just to see if it even compiles. Interesting. isn't in the tree. Is less than stairs dot length. Interesting. Our parent array pretty much says that every parent starts from start. Which doesn't make any sense because after that, okay, we'd say that, okay, v does not equal w. Distance sub w would be infinity. Infinity is greater than 0 plus 4 or whatever it is. Okay. We can see that those values are being set here. Now we're going to say dist is equal to infinity. We're going to select the next vertex to process that isn't in the tree. For let w equals 0. And, oh, wait. This should be w. If w isn't in the tree and distance is greater, which is infinity, distance of w, yes, I would say dist is equal to distance of w. We should end up choosing this node here. And then v would equal w. Or pretty much we should end up choosing this node at the end. And then from there we should end up choosing, that one is in the tree, so now we put it into the tree. Let me print in tree as well. Okay, so now we're at the last node in the graph, iterating over the neighboring edges, which is all of them. I see. Pretty much we end up choosing I see. We do end up visiting the whole graph, but 0, it's kind of hard to beat 0. So we would just choose ourselves. We would just choose 0 again. How is this even avoided on other algorithms? Or how is it even avoided on regular Dijkstras? I feel like something's wrong with my Dijkstras. Oh, wait. Yeah, I'm gonna have to read a little bit more, and then I think we'll be back tomorrow.